Okay, PD10. So this is about the heat equation. This is another one of these partial differential equations. I mean, again, it's kind of like a differential equation, except it involves partial derivatives. We call it a partial differential equation, or a PDE. Right? So we have a PDE here, and this describes how heat flows in a system. And by the way, this is very physical. And I don't know, I wish I knew more about what types of stuff engineers do, but in physics classes, you'll study this, thoroughly. In fact, I correct myself. I do know y'all are going to see this in Math 108. Now, this is what I've shown you here. This is the three-dimensional heat equation. You might only do the one-dimensional heat equation in Math 108. But the point is, we're not going to actually derive the heat equation or show general techniques for solving the heat equation. I'm just giving you a function, and we're just going to check that it works. So this is a much easier version than what you're going to see in Math 108. Although it is three-dimensional. So the idea is we have this heat operator. So the convenient notation for it is to just write that. But what it means is that this is an operator that does to a function u the following thing. It takes the partial derivative of that with respect to t and then subtracts the Laplacian of that thing. So that's just the notation. Okay, so we want to show now that the heat equation is that this heat operator applied to the function equals 0. We want to show that that heat equation is satisfied by the following function. And it's a much to write down here. But k equals, okay, t to the negative 3/2 e to the negative x squared plus y squared plus z squared divided by 4t. We want to show that this, when you stick it in there, we want to show that that equation works. Okay. Now, just for the record, just so you know, so a quick physical connection, what's going on here is this describes, if you look at the exponent, now this is just a correction factor to make the algebra actually work, but if you look at roughly what you've got here, this is kind of one of these normal, what do they call them, normal distributions that you guys might have seen way back when in Math 32, so because you've got e to a negative quadratic. And you remember that this denominator here relates to the standard deviation, so how wide is the thing. And as what this is saying is that as time passes, the width gets higher. And so in particular, if you start off, if you've got heat localized at one spot, so it's hot here, but it's cold everywhere else, what this is saying is that that concentrated heat kind of spreads out over time. And it spreads out in exactly this way because this function satisfies this heat equation. And again, just a very, very quick thing, I claim that there is a fantastic physical motivation for why this is the heat operator, for why this heat equation has to be satisfied. And in your engineering or physics classes, if you see this equation, you might get to see why that is. But here we're just going to do the algebra, and here it is. We've got a bunch of stuff to compute. First I have to compute the partial of k with respect to t. It's just algebra, right? It's a bunch of algebra, but you got to take the partial of this thing with respect to t. And what's annoying is that there's a factor of t here, and there's a t in there, so you got to use the product rule. And all right, here we go. So first we take the derivative of this factor, and then multiply by this. And then I have to add the original factor, t to the negative 3/2, times, now I've got to take the derivative of this with respect to t, which of course is itself and now I've got to multiply by the derivative of all of this exponent with respect to t, and let's see here, that's going to be I kind of ran out of space here. The derivative of this exponent with respect to t, we've got t to the sort of the -1 here, so I claim we're going to have x squared plus y squared plus z squared over 4t squared. If I've done my algebra right there. That look right? Okay. All right. So that's the partial of k with respect to t. Now you get to compute the Laplacian of this thing, and here's where I'm about to punt and let you guys finish it up. But this is just a bunch of algebra. So the Laplacian of k. Okay, well, good news. At least you don't have to use the power rule that much, right? But you are going to have to compute three things. Yeah.
Okay. You only have to compute x, y, and z, not t.
Do what now? Oh, for the Laplacian, yeah. Yeah, the Laplacian is, yeah. So here's the Laplacian, and it's the partials.
I thought it was like for all the inputs, though.
Well.
Because t is one of the inputs as well.
No, I get you on that. So t is as a time input. This notation. This is sort of standard notation usage here. That the Laplacian here means with respect to all the spatial dimensions.
Oh.
Yeah. So good news. A lot of the calculations you have there are still valid, right? You just have to scratch off that other term. Yeah. Yeah, so this is just the second partials with respect to x, y, and z. Yeah, I can see how you'd misunderstand that, and maybe I should write a comment on here about specifically that this is the second partial with respect to just the spatial dimensions.
I guess then I ended up taking the second derivative of the dk dt and all that junk.
Yeah, I understand. Yeah, right. So so you could just scratch that off. Yeah, right. So, okay, so let's remember, so I have to compute now the second partial of k with respect to x, and the second partial of k with respect to y, etc. And, you get, yeah. Oh, sorry, yeah, yeah. No, screen. Yeah. All right, so you got to compute these things. Can you do these things, or you want me to, maybe, why don't I get you started on one of these? Let me do the z second partial. So we need to take the z partial of this thing, and let's see, what is that? Well, the z partial of this thing. Well, okay, well, there's t to the -3/2. That stays there. The z partial of all of this is going to be this exponential. Now I've got to multiply by the partial of this with respect to z, which is just -2z over 4t. And now when you take the z partial of this, product rule. Right, so you're going to have two terms here, so it's going to be a little tedious, right? But it's just a matter of taking a deep breath, writing it down, and not letting the volume overwhelm you. Yeah. Right. So that's the z second partial, the x and the y also. And I claim that when you write all these things down, add all of them up, everything cancels, and in fact, this does end up equaling 0. Okay. Any other questions about this problem? Okay. All right.